Hmm. So in my last class, I just discussed about the very basic idea about the AC bridges. Okay. So we discussed about how it is related to Western Bridge. Okay. So in case of AC bridge, we are considering, that means we are going for the balancing. Okay, so both the side we are balancing. Here we are using some detector. Okay, so and we are getting the null point. Okay, so at balance condition, these B and C point, these 2 points are in equipotential points. Okay, so there will be no current flow, no current is flowing through the detector D. So we can say like that these 2 points are the equipotential point. Okay, equipotential points. Okay, so equipotential points, so we can say like that it is balanced condition. So what happened, I1 equal to I3, and your another thing, I2 equal to I4. So I1 equal to I3 and I2 equal to I4. This is the conditions at balanced one. That is another first condition. Second condition is that that is second condition. Okay, first condition is that here it is written V1 equal to V2. Okay, that means the potential of V1 and V2 both are same. And second condition, V3 potential and V4 potential both are same. Okay, so and you know that V1, here you can see V1 which is V3. So if we add V1 plus V3, V1 plus V3, so that equals to V. Okay, so all the components you can see it is written in uppercase. Okay, uppercase. So these all the components are written in RMS. Okay, these all are written in RMS. Okay, not instantaneous value. Okay. So these all are the RMS. Okay, that point we have already discussed. Okay, so the V1 equal to V1 plus V3 equal to V. Similarly, this equals to what? V2 plus V4. Both are in same. V2 plus V4. Okay, this is first condition and this is second condition. Okay, both are same. Then we are equating that impedance, then matching was there. Okay, then after doing the matching, we have observed that Z1 Z4 equals to Z1 Z4 equals to Z2 Z3. Okay, so all the cases that bar is there. Okay, so bar means now you know that is amplitude. Okay, so amplitude and argument. So Z1 bar equals to what? Z1 with the angle of theta 1. So Z1 with the angle of theta 2. Z4 with the angle of theta 4. Z2 with the angle of theta 2. So multiplications of angle means component means angle will be adding. So finally it is coming Z1 Z4 the angle of theta 1 plus theta 4. Z2 Z3 with the angle of theta 2 plus theta 3. Okay. Then we discussed about this numerical problem. Okay, so all the components was given, then finally we have find out what is the nature of that impedance. First we are going to find out that impedance, that Z4. Okay, so now angle is leading, so finally we are getting that it is inductance. Okay, the impedance indicate that was a series combination of resistance and inductance. Okay, so that we have discussed. Okay, that point we have discussed in my last class. Okay. Then we discussed about that the Maxwell inductance base. Okay, so find out what unknown self inductance. What type of inductance? Unknown self inductance. Here L1. That two portions R1 L1 is unknown self inductance. Okay, so we know the formula. Okay, so what Z1 Z4 equal to Z2 Z3. I hope that was the formula here. Z1 Z4 equals to Z2 Z3. Okay, so then we need to find out what is your Z1. Z1 is as simple as it. Okay, so impedance we have to find out. Okay, so R1 plus J XL1. Okay, sorry, R1 plus J XL1. Okay, so what is XL1? Actually, R1 plus XL1. So XL1 equal to J omega L1. Okay, so that you have written over there. That the value of Z1. Then what is your Z2? Z1, this is Z2. Z2 equal to what? You know that R2 plus XL2. So XL2 means what? XL2 J into omega L2. So you replace that value over there. So you know that Z1, this is Z2. R2 ZXL2. Then Z1, Z2, Z3, Z4. This is Z4 equals to Z3 directly resisting. This is Z4. Okay, if you replace it, then cross multiply. You are doing the cross multiplication. Finally, we will get the relation. Okay, so you are getting the relation that unknown quantity can be calculated by this way. So L1 equal to L2 into R3 by R4. R1 equal to R2 into R3 by R4. Directly you are able to find out the value of L1 and R1. Okay, so directly you are getting find out. Now the most important thing is the phasor diagram. I hope all of you are able to understand. Am I right? Hello.
Yes, sir.
Yes, okay, good. So when we are going to draw the phasor diagram, so this is very simple. So for phasor diagram, what we need to do? First, we need to find out the which one is our reference one. Reference value should be considered in our x-axis. Okay, so you know that is our x-axis. It is our x-axis. Okay, so we are considering that I1 is our reference. Okay. I1 is our reference we are considering. Okay, so I1 at equilibrium condition, that B point and C point, it is written that at balance condition. Balance point condition means B point and C point are in equipotential point. So there will be no current flowing through the detector. So detector, there will be no deflection in the detector. Okay, so same current, that I1 current also flowing that AB branch, and same current also flowing BD branch. So same current is flowing I1 through this branch to here. Okay, and what is our first condition? What we have to find out that formulas. So you know that balance condition V1 equal to V2. So first condition is what? V1 equal to V2, and second condition V3 equal to V4. Okay, that is first condition. And what is this? Another thing is that V equal to V1 plus V3 or V2 plus V4. Okay, same thing. So first I equal to what? You have to plot the V1. V1 equal to what? I1 R1 plus J I1 omega L1. Okay, so I1 R1 should be in phase with your current I1. So here you are considering current I1. So what is your I1 R1? So it is in phase. I1 R1 is in phase with your I1. So up to this point drawn you have drawn I1 R1. Okay, this is your I1 R1. Then what happened? J J omega L1 into I1. Okay, so J component means 90 degree. Okay, ahead. So it is written in this. That is your, what is the value? Omega I1 L1. Okay, so you have reached over there. So you have to, if you add them, so what value will get? V1. If you add these 2 points, you will get the V1. Okay, so you have getting the value of V1. Now you know that at equilibrium condition that we have written V1 equal to V2. Okay, at equilibrium condition we have written that V1 equal to V2. That one, V1 equal to V2. So here we have reached up to V1. This is our V1. We know that V1 equal to V2. If V1 equal to V2, then what is the value of V2? You know the value of V2. V2 equals to what? V2 equals to this one, I2 into R2 plus J omega L2. Okay. So equal to what? I2 R2 plus I2 J omega L2. Okay. This is our V2. So I2 R2 and I2 both should be in phase. Basically in resistive path there will be no changes. Okay. So you know that same path I1 and I2 both will be in same path. Then why both are will be same path? So basically both are V1 equal to V2 and they are also following same way. So I2 also be the same path. So you know that path also following I1 R1 as well as I2 R2. Then what happen again? 90-degree leading will be there. These points. Okay. So it will coming. You know that V1 equal to V2. So similarly same path will be superimposed equal to omega I2 L2. Directly it is coming omega I2 L2. So add them, so you will get that V1 equal to V2. Okay. So now you need to find out which one. Then V4 and V3 you have to find out. V3 equal to what? V3 equal to I1 into R3. So it will be in phase with your I1. So I1 is there. This is your I1. So V3, V4 in case of V3, V4. Okay, so there will be in phase. Up to this point you are considering I1 equal to R3. I1 R3. This is I1 R3. This drop I1 R3 equal to I2 R4. Why I4? Because V3 equal to V4. You know that V3 equal to V4. So that point is coming. So now you are adding that V1 plus, you know that V equal to what? V equal to V1 plus V3. So V equal to V1 up this point plus V3. So dotted line is there. So you will get the value of V finally. This is your final magnitude of the voltage. Similarly, that also similar to V4 plus V2. I hope all of you will to understand. That is called Maxwell self-inductance. Okay, Maxwell inductance bridge for measuring the self-inductance. Okay. Next, we are considering that Maxwell inductance capacitance bridge. Okay. So Maxwell inductance capacitance bridge means what happened? So here we can see it is Maxwell's inductance capacitance bridge. Okay. So what is written over there? The unknown inductance. So normally we have find out that unknown inductance is measured by the comparison with the standard variable capacitance. So here you know that standard variable capacitance, that C4 is there, standard variable capacitance. So arrow mark is there because that is varying in nature. It is much easier to obtain the standard value of variable capacitor with acceptable degree of accuracy. Okay, benefit is that accuracy. The unknown inductor L1 of effective resistance R1 in the branch AB is compared with the standard known variable capacitor. Okay, C4 on arm CD. The other resistance R2, R3 and R4 are the known as non-inductive resistor. That is very important. Non-inductive resistor. That which one is R2? That is your R2, R3 and R4. All are in non-inductive resistor. Okay. Now we have to find out varying the C4 and R4, giving the impedance as setting. So now we are varying that R4 and C4. Okay. So as simple as it, you know that Z1 equals to, you know that, sorry. So you know the basic thing. Okay, so what is our basic thing? That you know that Z1, Z4 equal to Z2, Z3, or Z1 by Z2 equal to Z3 by Z4. What is your Z1? Z1 equals to R1 J, that is your Z1, R1 plus J omega L1. Okay, Z1 by Z2. What is your Z2? Sorry, Z1 by Z3. What is okay? I'm wrong. Z1 by Z2. So here you are written that R2. Here it will be R2. The cross multiplying, interchanging is there. Okay. So finally you are getting that what Z1 by Z3, that is R3. Okay. So just for a moment. Okay, so so Z1 by Z3. So what is our Z3? It is R3 written. Okay, so Z2 is our R2. This is our R2, and Z4. Z4 means parallel of R4 parallel X C4. Okay, that is parallel. So you know that parallel means multiplications. You know that R4 parallel XC4. So means multiplications plus addition. Okay. So you know that R4 by 1 by J omega C4. R4 plus 1 by J omega C4. Okay. You can do the cross multiplication. So denominator will be, so it is cut each other. So upper side R4 will be there. Cross multiplications J omega C4 R4 plus 1. Okay, I hope all of you will to understand. Okay, that directly it is written over there. Okay, that is Z4. Sorry. Okay, that is all Z4. I hope all of you will to understand. Okay, so now they are cross multiplying. Okay, after cross multiplying you will get that you will get an identity. Now you are comparing the real part. Okay, now you are comparing the real part. What is your real part? These two are the real part. Okay, and another two are the imaginary part. So which are the imaginary part? These two are the imaginary part. Okay, so now you are equating. Okay, now you are comparing the imaginary part and real part. So here you are comparing the real part, and finally you will get the expression R1 equal to R2 into R3 by R4. Then you are comparing the imaginary part. So here you are getting that L1 equal to C4 R2 R3. Okay, so you know that unknown inductance, that is your unknown inductance, and the impurities of the unknown inductance. So both the cases L1 you need to find out, R1 you need to find out. So here you will get the expression of R1 and L1. Both the expression you are able to get. Okay, now the most important thing is that phasor diagram. So in the phasor diagram, so which one of the parameter you have to consider as reference? That should be in x-axis. So I1 you are considering in the x-axis. So similar thing, I1 R1, first you have to plot the V1. What is your V1? Okay, so V1 equal to what? I1 R1 plus, okay, I1 whole divided by J I1 L omega L1. Okay, so it is J I1 omega L1, so 90 degree, this one. So it is your V1. You will get the value of V1. Now you know the V1 and V2 both are same, so equating that V1 equal to V2. I am writing V1 equal to V2. V2 equal to what? You know that V2 equal to I2 R2. So I this is your V2. Okay. So I2 R2. So it's a resistive part. Okay. In resistive part, there is no difference in between voltage and current. So if this axis is for V2, so I2 will be which axis? Similar axis. Extension of that V2. This is your I2. Okay. So V2 I2 should be in phase. That's why this is your I2. Okay. Now you'll get the value of I2. Now I2 equal to what? I2 equal to, you know that two currents are there, IR and IC. IR into IC. Okay. So you have to find out I2 equal to vector addition of IR into IC. Okay. So that point will come. Okay. That point will come, which is the direction of IR, which is direction. So first I1 direction we will get I1 R1. Okay, then we have to plot that V3. V3 equal to what? I1 into R3. V3 equal to I1 R3. So I1 axis is this is I1. So V3 equal to, so it is V3 equal to I1 R3. Directly we have written I1 R3. Now V3 equal to V4. V3 and V4 equal to some. At equilibrium condition, what are the things? V1 equal to V2. V3 equal to V4 and V equal to V1 plus V3 or V2 plus V4. That's the condition, simple condition. Okay. So now equilibrium V1 equal to V3 equal to V4. So this is our V4. V4 equal to what? So this axis is our V4 axis. Okay, that point V4, V3 as well as V4. So you know that V4 equal to what? V4 equal to, it is IR I4. Okay, V3 equal to V4. This is I1 R1 and V IR R4. So I1 and IR both will be in phase. There will be resistive path. So that's why this is IR. IR also in this phase. Okay, that's why this point is IR. Okay, now you know that IR plus IC equal to I2. If you add these 2 points, so you will get the value of IC. Okay, and that IC you are getting. So V4 also V4 equal to what? IC into XC. This is similar to IC into XC. XC4. So what is XC4? IC by J omega C4. So that also been connected, that J, if you coming that point, so it will be coming minus IC J omega C4. So that also been similar to V4. Okay, so it is lagging. I2 is there, so minus means IC is that axis, so minus means it is 90, minus 90. From IC to this point is minus 90. So I hope all of you are able to understand the phasor diagram. Is there any doubt? Hello, is there any doubt?
No, sir. No, sir.
Okay, good, very good. Okay, so we can go for the next one. So what are the most important understanding from this diagram we can understand? Okay, so that ideal inductor. So first understanding is that ideal inductor will lossless. Okay, but what happened in real inductor, that you know some impurity is there. So that's why one unknown resistance means impure resistance, that R1 was there. Okay, so real inductor having some non-zero resistance. Okay, non-zero resistance. Due to resistance, the metal wires should be the inductor winding. So that's why that problem is there. The series resistance caused the generation due to power loss. Definitely I square loss will be there, additional power loss, that is not considering normal cases. But if you consider in ideal cases, that resistor value tends to 0, but actual case that resistor is present. Okay, so in such case the quality factor, okay, the quality factor, that means the Q factor of such lossy inductor is used to indicate how closely the real inductor comes behavior in ideal inductor. Okay, that we can understand over there. The Q factor of that inductor is defined as the ratio of its inductive reactance. Okay, I think all of you will understand the ratio of the inductive reactance. Okay. The ratio of that inductive reactance registers given frequency. Definitely the frequency is another important issue. Frequency. First, I have discussed about that Wheatstone bridge normally we are using for measurement of unknown resistance. Okay, in that case that was DC bridge, but here we are using AC AC bridge for measurement of unknown L, C and sometimes frequency. Basically, why frequency? Frequency also related to L and C. Means the value of XL and XC directly related to our frequency. Okay, that's why three components we can directly measure by using that AC bridge circuits. Okay, that's why the given frequency also important. Changing of the frequency is not means it should not be considered. If you take that frequency fix, then do the other thing. Q factor is measure of the efficiency of inductor. Okay, efficiency of inductor. Higher values of Q factor, the closer it approaches the behavior of an ideal lossless inductor. An ideal inductor would have an infinite Q, okay, at all frequencies. But practically it is not possible. It is shifted from here. It is Xc equal to Q equal to omega L by R. So Q factor it is written omega L by R. Okay, so that is shifted. It is Q equal to omega L by R. Okay. The Q factor of the inductor is given the formula Q equal to omega L by R, where R is the internal resistance R, C is resistance, and omega L is the inductive resistance, inductive reactance given frequency omega. Q factor of an inductor can increase by either the increase of the inductance value by using the good ferromagnetic core or by reducing the winding resistance by good quality conductor materials. Okay. In special cases, maybe the superconductors as well as. Okay, Maxwell inductance capacitance means that means Q factor inductor under measure can be found the balance condition to be. So you just written find out the value of Q. Okay, Q value you need to find Q equal to omega L by R. Okay, so sometimes if it is XC, so what will be the relation that is given for there. So if you replace the value of L1 and R1 from that Maxwell inductance capacitance bridge, so you will get that value. Okay, omega C4R4. So find out the Q is another important problem. Okay, means important factor. What is the advantages of Maxwell bridge? Okay, we need to know about the advantages. Balance condition are independent to each other. Two variables C4 R4 can be varied independently. That is first one. Second one, final balance equation are independent of the frequency. If you not changing the frequency or changing the frequency, you will get the value independent of the frequency. Okay, so if you changing the frequency, no matter whatever inductor or capacitors are there. Okay, so that's another important notation, means notification observations. The unknown quantity can be denoted the simple expression involving known quantities. All are in known quantities. Balance equation is independent of the loss associated with the inductor. Definitely there is unknown resistance both the cases. So loss component always be there. Okay. So efficiency an important issue. Wide range of inductance, the power and audio frequency can be measured. So huge range of applications. So you can do for that audio frequency as well as power frequency. Means whatever frequency means high frequency application as well as low frequency application. Audio frequency means it will be within 20 to 20 kilohertz range. Okay, you can do the measurement this range to beyond this range. Okay, that's it. So disadvantages, we are discussing about the advantage and disadvantage. The bridge for the operation require the standard variable capacitor. Okay, that variable capacitor is quite costly and it's not easily available. So very expensive. It is written very expensive. High accuracies are asked for it. Okay, in such case, fixed value of capacitor are used in the balance associated with R4 and R2. So two things are going to be varied, that is R4 and R2. Keeping the capacitor is fixed. Why? Basically, it is very expensive. That's the reason. Okay. This bridge is limited to measure the low Q inductor, that up to Q value you can measure up to 10. Okay. If you can go beyond that value, but the error will be more. Okay. That's why you should not go beyond the value of K, means beyond 10. Okay. U value beyond 10. So Maxwell bridge is also unsuited for coils very low value of key. Example Q is less than 1. Okay, such low Q inductors can be found as in the inductive resistor and RF coils. Okay, Maxwell bridge finds difficult and the laborious to obtain the balance of the low Q inductors. So that is another important problem. For low Q value, the calculations means the accuracy problem is there. Okay, means you have to design the points and means you have to select the parameters such a manner so accuracy will be, in that case you can see the accuracy will be less, very less. That's the point. Okay, so go for another bridge, so that is called Hayes bridge. Hayes bridge means previously we are doing for that Maxwell's bridge. Okay, that is for that is for low Q value. Now we are doing for Hayes bridge, that we can see for high Q value. Okay, how Q inductor value, measurement of high Q. Okay, so that one we are using by the Hayes bridge. Hayes bridge also associated the phasor diagram under the balance figures are given here. You know the diagram of figures. So in previous case, Maxwell capacitor inductor bridge. So R4 and C4 was in parallel with your R4. Now you are making C4 in series with your R4. Okay. So you know that value of Z1. So basic equations are same. Z1 by Z3 equal to Z2 by Z4. So Z1 equal to what? R1 plus J omega L1. Okay, what is written? Unknown inductor L1. So L1 is your unknown inductance. So you need to find out the value of L1. Okay. R1 is what? Impurities of inductor L1. The branch AB is compared with the standard known as the variable capacitor. That C4. The C4 again the variable capacitor from arm CD. Rest of the portions, rest of the values are standard values. Okay. So except your L1. L1 is unknown. L1, R1 you have to find out. That's why you will see over there. You are going to find out the value of L1 and R1. And finally, you will derive the value of Q. Q equal to omega L1 by R1. So you just replace the value of L1 and R1. You will just find out the value of omega. Okay, sorry, find out the value of Q. You know the one Z1 by Z3, Z1 by Z3 equal to Z2 by Z4. So what is your Z4? Z4 equal to R4 plus, okay, 1 by J omega C. Okay, you can 1 by J omega C means it will minus J by omega C4. Okay, directly coming. The cross multiplication is there. Now you are equating the real and the imaginary part. Real and imaginary part. Finally, we have received that R1 R4 plus L1 by C4 equal to R2 R3. So that we have getting over there, and finally equating the value. So we'll get the value of L1 R1, and then most important thing is that phasor diagram. So you know that V equal to what? V equal to V2 plus V4. Or you say like that V1 plus V3. V1 plus V3. Okay, and I1 balance condition. These 2 points are equipotential points, so no current flowing through this detector. Okay, so I1 equal to I3 and I2 equal to I4. Okay, so both the cases I1 and so first, which one you have to consider? In each and every condition, we are considering that I1 is a reference. I1 over there. Okay, now you have to find out that value of I1 R1. So definitely I1 R1 should be in phase with that value. So it is your I1 R1. Okay. Then J omega I1 L1. So it is your omega I1 L1. So you will get the value of V1. Directly we will get the value of V1. Now you know that V1 equal to V2. V2 equal to what? V2 equal to I2 R2, like your previous case. So it's the extension. So V2 is there means then I2 will be in this way. So it is your I2. Now you know that V1 equal to V2. Now V3 equal to V4. What is your V3? V3 equal to, you know that first condition is V1 equal to V2. Second condition is V3 equal to V4. So V3 equal to V4. What is your V3? V3 equal to I1 R3. So that point you are considering. So it is I1 R3. V3 equal to V4. Again V4 equal to what? V4 equal to I2 into R2 minus I2J by omega C2. So I2 R2 minus that one. Okay. So what is your I2 R2? I2 R4. Okay, so you know that is your V4, that point is V4. So I2 is that point. So I2 R2 will be this side. Okay, that is your I2 R4 in phase with your I2. Okay, I2 is in phase of your V2. Okay, so you get the value of I2 R4. So that point I2, and it is your V3. Okay, so V3 equal to V4. V4 equal to what? V4 equal to also I2 R2 minus, okay, J I2 by j omega C2. So this value. Okay, or you say like that, this one parallel I2 by omega C4. Okay, or minus J. Okay, minus J and J I2 minus is there, so that's why minus 90 from I2 to minus 90. Okay, that 90 is there, it's minus 90. Rotation is left side. Okay, anti-clockwise. So you are getting that value lagging. That's a capacitive nature. That's a lagging. Okay, inductive means leading. Okay, capacitive means leading power factor. That means it is taking the VAR. Okay, inductor means it is lagging power factor, means providing the VAR. Okay, reverse thing happen. So I2 by omega C4. Okay, that is coming I2 by omega C4. Now you add them, so you'll get the V4. Okay, so you have the value of V3, V4, that point, and this point is your V1, V2. So these points. Okay, now you can add them, and finally you will get the value of V. Okay, I hope all of you able to understand. Am I right? All of you able to understand? Hello? Am I audible?
Yes, sir.
Yes, sir. Okay, so all of you able to understand?
Yes, sir.
Yes, sir. Okay, if you have any doubt, you ask me. So again, I will repeat. Okay. So now we can go for the next bridge, that is called Anderson bridge. Okay. So Anderson bridge, if you see the structure of the Anderson bridge first. Okay. So structure of the Anderson bridge is that. So it is, you know that first term is unknown. That R1, L1, R1 is your unknown one, but this R1 is your known value. Okay. And V3, that is your R3. Okay. So I1 R3, and here you can see that equipotential at balance condition, equipotential points are B and E. Detector is connecting in between B and E terminal. That B terminal and E terminal. That two points are equipotential point at balance conditions. Okay. So what happened? So first we know that Z1 value. Okay. If you see that expression, so first you know that at balance condition what is written, the modifications, it is modifications of Maxwell inductance capacitance bridge. Okay, this modifications. Okay, so in which the value of the unknown inductor is expressed in terms of the standard known capacitor. Standard known capacitor, this method is applicable for precise measurement. Okay, means accurate measurement of inductance over wide range of values. Okay, so what is given in the figure, what is given Anderson bridge configuration and corresponding the phasor diagram under the balance condition. So that phasor diagram I will going to be discussed. The unknown inductor L1, effective resistance R1. Okay, means impurities. In the branch AB is compared with the standard known capacitor C arm ED. Okay, which arm? ED arm. Okay, here we can see what is ED. That is our ED arm. Okay, so that arm. Okay, one capacitor C is connecting over there. So that will be balanced with that arm. Okay. Then the bridge is balanced by varying the value of R. So that impurities are there, varying the values of R. R is there. Okay. So this balance, they're doing that balance by varying the R. Okay, that value. Okay. So by varying under balance conditions, no current flows through the detector. Okay. Nodes B and E, node B and E are the same potential. So at balance condition, I2 equal to IC plus I4. So if these 2 points are same, so I2 will be what? I2 equal to At balance condition, the same current, there will be no current flowing over there. So IC current also flowing this path and I4. So at balance condition, what happened? I2 equals to IC plus I4. That will come. Okay, so normally we are considering the reference value. So I1 equal to x-axis, the I1 will be there. I1, so x-axis I1, so you have to find out the value of V1, simple. So I1 R1 plus R1, capital R1 plus lowercase r1, both are in series. So these points will be there. Finally we will reach that V1. Okay, now V1 equal to what? V1 equal to that this point up to this point. Okay, so V3 equal to, okay, what is your V3? V3 equal to I3 into R3. So if it is I1, so resistive path, so I1 and R3 will be same line. Okay, so rotation will be anti-clockwise. So V3 equal to I3 R3. So this point you are considering V3, I3 R3. Again V3 equal to what? IC into IC into XC. XC means IC by omega C. IC by omega C. So minus term also be there. Okay, so that term. So it is VC. That term also VC. So V3 equal to here in this equation, V3 equal to VC. Okay, V3 equal to VC. Okay, and V1 equal to your V2 plus ICRC. V1 equal to V2 plus ICR. IC into R. Okay, that's the conditions. V1 equal to V2. So what is your V2? That for V2 equal to again I2 R2. So you have to find out the value of current I2. So how to find out? Okay, so I hope you are able to get up to value of V3. V3 you are able to get. Okay, so V3, these points is your V3, these points is V1. So you will get the value of up to that point. So finally you have to find out the V1 plus V3 equal to V. Okay, so if you add this two, so V should come. Okay, but we have to find the other terminal also. So we know the V3 over there. V3 equal to again what? V3 equal to IC into what? XC. So that is IC by omega C. Okay, so this is okay. So what is the value of V4? V4 equal to I4 R4. Also V4 equal to I4 R4. Also V4 equals to, okay, that is IC. This is V4. Okay. So again, sorry, your I2 current equals to IC current plus I4 current. Okay. So what is your IC current? Okay, if it is your V3 equal to what? V3 equal to IC into XC. So this is your V3. Okay, so it will be leading now. So if voltage is there, current also capacitor current, it will be leading with your V3, which angle? 90-degree angle. So this current is your IC current. Okay, so IC into R also be in phase. This is IC into R. Okay, that in the axis of Y axis, this is Y axis. Okay, so IC into R over there, IC into R. Okay, and that you have already find out that point. That point you have already find out here. So if you add them, okay, directly you will get the value of V4. Okay, so we will get the value of V4 over here. Okay, that point. Again V4 equal to what? I4 into R4. V4 equal to what? I4 into R4. I4 into R4. Okay, so that means I4 and V4 should be in phase. Okay, I4 and V4 should be in phase. Now IC plus I4, that is IC plus I4. IC plus I4 equal to I2. Now you add them. This is your IC, this is I4. So if you add them, so you'll get the value of I2. This value is your I2. Okay, now what is your V2? I2 into V2. Okay, I2 into R2. So you'll get that value I2 into R2. It is your V2. Okay, So you know that V1 equal to what? V2 plus IC into R, that is your V1. So it is your V2 up to this portion, it is V2. Then you add that point, okay, up to this portions, up to this portion it is V2, up to this portion it is V2. Now what is your V1? V1 equal to V2 plus ICR, IC into R. So parallel this point, this is ICR, so you'll get the V1. So it is means coincide all the thing. So directly V1 you will get this point, V2 will get this point, it is your V4. Now what is your V3? V3 also being calculated, V3 equal to this point. So 4 points are there, V1 is there, V2 is there. What is your, where is your V2? V2 equal to I2 R2, that means this point. So V1, V2, V4 and V3, all 4 points you have able to get. Now you add them, you directly get the value of V. Okay, I hope all of you are able to understand the Anderson bridge. Okay, the entire equations are written over there, and I have discussed from the phasor diagram how you will get the value of phasor diagram. Okay, the important portion is written over there. So if you go, if you are able to go through it, so same thing, whatever I am telling you, so that is written over here. Okay, if you have any confusion up to Anderson bridge, is there any confusion up to Anderson bridge? Hello?
No, sir.
Are you able to understand?
Yes, sir.
Yes, sir.
Okay, very good. So then we go for the next one for measurement of capacitance. So by using Maxwell bridge, we are going to find out that unknown inductance. Then we are using Hayes bridge for getting that more value of Q for unknown inductance. Okay, Maxwell bridge having two types. Okay, only inductance type, then capacitor inductance type, then Hayes bridge. We are using that series resistance, series capacitance with the resistance. Then we have discussed about Anderson bridge for find out that circuit means accurate for getting that accurate measurements. Okay, so we are using the Anderson bridge. After that, we'll discuss about the measurement of capacitance. Okay, so unknown inductance by using, okay, by using known value of the capacitance by using Owen's bridge. Okay, so the bridge measurement by using the unknown inductance in terms of known capacitance value. The diagram is given over there. Okay, so configuration corresponding phasor diagram under balance condition, you know that is very simple. So balance condition means Z1 Z1 Z4 equal to Z2 Z3. Okay, so that's the conditions. So directly you will able the you will able to get the value of Z1. Okay, so that is Z1 by Z3 means R3, that is your R3 directly coming Z1 by Z3, and it is your Z2. Z2 means this value, Z2 means R2 parallel X C2, means R2 parallel 1 by j omega C2. Okay, so R2 into 1 by j omega C2, R2 plus 1 by j omega C2. So cross multiplication will be there. So R2 by j omega C2 R2 plus 1. Directly will get it. So this value is there. Another one, that capacitor Z4. Okay. So 1 by j omega C4. Okay, so phasor diagram is as simple as it. So one thing will be there as a reference. So I1, always you are considering the reference. So I1 R1. Okay, then this point is your V1. V1 equal to what? V1 equal to V2. You know the V2 equal to I2 R2 plus 1 by j omega C2 into I2. I2 will be in numerator. Numerator. Okay. So as simple as it. So V1 equal to V2. You know that value is V2. Okay. V2 equal to what? I2 R2. Okay. So you need to find out the value of I2. Okay. So I2 R2 and j omega C2. So you know that I2, if it is I2 R2, 90 degree leading, So if 90 degree, in that case 90 degree behind means you will get that value of V. So that points is your I2 by omega C2. Okay, so you know the find out, you can able to understand that the direction of the current I2 is in Y axis. Okay, so this is your I2 and I1 is over there. Okay, you are able to find out the V1. Now where is V3? V3 equal to I1 R3. That is V3 I1 into R3. Same phase with your I1. It's a resistive path. Equals to I2 by j omega C4. Okay, j omega C4 I2 by j omega C4. So again I2 you know that is leading with that with the angle of 90. Okay, so from here you can easily understand 90 degree leading. Okay, I2 is 90 degree, sorry, I2 is 90 degree leading with your angle. Okay, mega. So as simple as it, so it is your V4, so add them, so you'll get the value of V. So simple thing, simple calculation. So for balance condition varying R2 and C4 independently, we will able to find out the value of R1 and L1. After that, you can calculate the value of Q omega L1 by R1. Replacing the value, you will get the value of Q. Okay. So after that, you will have the measurement of capacitance. Okay, so few portions are there. So measurement of capacitance I will discuss in my next class. Okay, so up to measurement of inductance, I hope all of you able to understand. If you have any query, you can ask me. Okay, so we can rediscuss some of the portion. Okay, if you have any query, if you have any problem, so I can rediscuss some of the point. Okay, do you have any kinds of query? Do you have any kinds of query?
No, sir. No, sir.
Okay. 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 So okay. So we'll say today I'll stop here. Okay.